Now, the probability of achieving population inversion increases because we are having a metastable state to be present, which has a quite great lifetime when compared to that of what? An excited level. Clear? So now what happens? Whenever I pump my atoms, it transits from the ground level to that of the excited level, and from the excited level, it undergoes quick transition to that of the metastable state. Clear? Now, the probability or the lifetime of the metastable state is quite stable when compared to that of the excited condition, that is the excited level condition. So this makes a population inversion to be achievable. Okay. Now what happens when we compare the number of atoms present in my ground state to that of the metastable state? We achieve the population inversion condition. Thereby, the number of atoms will be more in metastable state than compared to that of what? Ground level state. Clear? So this is what population inversion is. Now, what happens since we achieve population inversion? We find lacing action to be produced between metastable condition and ground level state. Clear? Now, the difference for a 3 level and a 4 level laser is, if I go for a 4 level laser, I find two intermediate levels between ground state and excited state, and one level above ground state condition. Clear? And the lacing action takes between these intermediate levels, these two intermediate levels. Clear? So the difference what we are going to try to create here, the pulsed output what we have obtained previously will be rectified here to produce a continuous output. So the output of the 4 level laser will be always continuous. Reason, in 3 level laser population inversion is achieved, but after pumping. Clear? After I find lacing action to be produced, again the number of atoms in the ground level state tries to increase, so that I need to go for again a pumping action. Okay, so this gives a dead time in my laser action. Clear? So I need to pump again, either by optical means or electrical means or whatever. If I exert to that of the excited condition, what happens? It creates a dead time, which creates an output with pulsation. Okay, this is what the reason why we get a pulsed laser in a 3 level system. Whereas in a 4 level system, since we find the population inversion between intermediate levels, we know that the metastable condition will have quite lifetime greater when compared to that of an excited level, whereas the lower level, which is present above the ground state, will have much lesser lifetime. So what happens is, the atoms which are present in my lower level above ground state will try to undergo transition continuously. So more or less the value will be equal to 0. So the number of atoms in my lower energy state are nearly equal to what? 0. Okay, so 0 is my condition always. So whenever I find the inversion condition between these intermediate levels, since one of my level is going to be having the number of atoms to be 0, this population inversion will be present for all time intervals. Okay, that means my pulsating laser will don't have any dead time. You will find what? Continuous pulses to be produced. Clear? So this is what the understanding should be. Hope I made this clear for you. So is that clear for everyone? Yes, no? Answers please. So you need to understand things. Yes, no? Answers. Kindly put it in the chat box so that I could understand whether you have understood or not. Clear? Yes, am I audible? Okay, thank you. So remember these things. In laser, by stimulated emission of radiation. So this stimulated emission of radiation is going to be get initiated with what? A spontaneous emission. And don't forget this, my stimulated emission is going to be created by means of what? one photon that is emitted by spontaneous emission. Then spontaneous emission is not accounted for. You will go for what? Stimulated emissions. And that particular photon will trigger all of my stimulated emissions across my excited conditions. Clear? So this is what a laser is. And for light amplification, we put optical resonators. Optical resonators are nothing but what? Two mirrors. One is fully mirrored, another one is partially mirrored. So between these, the photons will try to travel back and forth to create more energy, to create more stimulated emission, to create more absorption. All these happens, high energy profile will be created, and then what? The light energy leaves as a coherent beam from the partial mirror. Clear? So this is what we have been seeing. Okay, so we have completed how the laser is going to work and what is 2-level laser, 3-level laser and 4-level laser. Okay, now we are going to talk about the properties of laser. So we know about the properties of laser briefly, right? So what are those? The first one is directionality and divergence. That is, directionality and divergence are correlated. Clear? And second point is monochromaticity, and third is coherence, and fourth one is going to be intensity and brightness. So these are all the things that we are going to study in detail in characteristics of laser. So we can compare a normal light, that of a laser one, by means of what? These four things. Clear? So we are going to talk about directionality, monochromaticity, coherence, and the fourth one going to be intensity. Clear? So this might not be mentioned, so kindly note it down. The characteristics of laser is being associated with directionality and divergence, first point. And second point is going to be about monochromaticity. And third point is going to be about coherence. And the fourth point is going to be about intensity and brightness. Clear? Okay. Now, coming to directionality. When a laser beam is being put away, okay, put away from an optical resonator, it is going to be expressed in terms of full angle beam divergence. The answer is, it is going to be expressed in terms of what? Full angle beam divergence, which is twice the angle of the outer edge of the beam. Okay, so we find a beam to be produced, and this outer edge of the beam is going to be related with beam divergence with twice the value. So that is what we are going to have it as directionality. Okay, we say it as 2 times theta. Okay, okay, that is how it is going to be related. So directionality and divergence is going to be a one phenomena. Okay, so you understand about directionality, you understand about divergence of the condition of the laser. Okay, now take down this point alone. A directionality of a laser beam is expressed as given in the point. Directionality of a laser beam is expressed in terms of full angle beam divergence, which is nothing but what? Twice the angle that the outer edge of the beam makes. So when a beam comes out, it is going to be related with full angle beam divergence with twice the value that angle has been made by the outer edge of the beam. Clear? Okay. And that will be with respect to the laser beam. Okay. So this is what you need to understand from directionality. Now, the outer edge of the beam is defined as a point which the strength of the beam drops around 1 by E times its value at the center. So when I have a certain value at the center, that is, we are talking about the strength of the beam, the intensity of the beam at the center. So when we compare that, the outer edge to be found, this outer edge will have 1 by E times of exponential dropping with respect to that of the strength at the center. So that is what you need to understand. So the outer edge of the beam will have what? The strength of the beam to be dropped to 1 by E times, 1 by exponential times with respect to that of the center. Clear? Now next, at D1 and D2 distance from the laser window. Say take for an example, we are trying to find D1 and D2 distance from the laser window. And if the diameter correspondingly for D1 is to be noted as A1, okay, and for D2 we are going to have a diameter as A2, then the angle of divergence phi is given by A2 minus A1 divided by 2 of D2 minus D1. Clear? Okay. So it is going to be related with the diameters. Again, diameters of the spots. So I can relate my distances to that of the diameters. Clear? So the distances D2 minus D1 will be given by what? 2 times psi divided by A2 minus A1, the diameters, or we can say it as simply psi is equal to, or the beam divergence is equal to, related by diameters difference A2 minus A1 divided by 2 times of what? D2 minus D1. D2 and D1 are a certain distances from point from the laser window. Okay. So if I have a laser beam, if it is being projected to a window, and if that window is kept at distance D1 and D2, and at that particular distance D1, if I get a diameter of A1, and at particular distance D2, if I get a diameter of A2, then this beam divergence can be expressed as psi is equal to, or phi is equal to A2 minus A1 divided by 2 times D2 minus D1. Clear? So this might be easier for you to understand. So at different distances, if my diameter changes, it is going to be related with what? The divergence. So you understand both directionality and divergence from this phenomena. Okay. If I have very less divergence, I will have more directionally pointed wave. If I have more divergence to be produced, my directionality gets reduced. So both are related one another. Okay. For a typical laser beam, the beam divergence will be in 1 milliradian. So that is what you need to understand here. So my beam divergence is going to be in the range of what? It is going to be in the range of 1 milliradians. Think about that. 1 milliradians is very much lesser. Okay, and that is how directional the laser beam is. How directional and less divergent the laser beam is. Clear? Now coming to monochromaticity. So you know about monochromaticity. Monochromaticity is a best property that is going to be associated with the laser condition. Clear? So this monochromaticity is nothing but what? It is going to be of relation with a wavelength. I am going to produce a single wavelength. Okay, and that is what monochromaticity is meant to be. Okay, the degree of monochromaticity is expressed in terms of line width. Okay, it may be of the spectral width. Okay, the bandwidth of wavelength to be produced. So the line with this frequency spread del V of a spectral line. So we are going to take a condition. The line with this is this frequency spread del V of a spectral line. The frequency spread del V is related to the wavelength of wavelength spread given by del lambda. Sorry, here it is wrong. It is going to be as del lambda. So del lambda is equal to minus of C divided by V square times del V. Okay, so del V is the frequency spread. It is going to be related with del lambda. So we are talking about monochromaticity here. Monochromaticity means to be about the wavelength. Clear? It is about single wavelength. So the change in wavelength is going to be related with change in frequency, which is given by del lambda is equal to minus of C divided by V square times del V. Okay. Now, when we speak about monochromaticity, you need to understand that broadening happens even though we have a laser light to be produced. This laser light, even if it has more monochromatic conditions, it still have some broadening conditions happens because of certain processes. Okay, that is what we are going to deal in detail. So we can see the monochromaticity is going to be affected by Doppler broadening, collision broadening, and natural broadening. So hope I made this clear for you. So the monochromaticity condition will be affected by three of these broadening things. Okay, and those three are nothing but Doppler broadening, collision broadening, and natural broadening. So when we talk about this Doppler broadening, why does it happen? It is because of the atoms which emit radiation. Okay, and they are not at rest. at the time of emission, they will move with the velocity. Okay, so that is what you need to understand. Because of these change in velocities and direction of motion, what happens is your radiation changes slightly and gets broadened. Okay, so that is what Doppler broadening is. Doppler broadening is about the atoms which emit radiation. Again, these atoms which are not at rest during the time of emission will move with the velocity and direction. And these velocity change and direction with respect to other atoms, other set of atoms, will create what? Radiation changes with respect to an happening of broadening. We call that as what? Doppler broadening. Okay, so this is what you need to understand. Doppler broadening is going to happen at atoms which emit radiation. Okay, and these will move at a velocity and direction of motion and with other atoms, with other excited atoms which undergo emission. During these, the frequency of emitted radiation changes because of that, and slight broadening takes place. We call that as Doppler broadening. So, what you need to understand is, if I say about Doppler broadening, it is going to be because of the velocities and direction of motion of the atoms which emit radiation. So, that is what you need to understand from Doppler broadening. Clear? Now, collision broadening. Now, these excited atoms, which if at all if it undergoes collision at the time of emitting radiation, then there will be a change in phase of the emitted radiation, resulting in a frequency shift and also accompanied by broadening. So these we call it as collision broadening. So in collision broadening, as the name gives us, collision is going to take place at the time of emitting radiation. Clear? So during the emission of radiation, if the atoms undergo collision, okay, we will find some of the phase to be shifted, resulting in a complete frequency shift and broadening of the light wave. We call it as collision broadening. So we have seen two broadenings that may affect my monochromaticity. Okay, if my frequency pattern changes, it will also affect my wavelength. Clear? So that is what you need to understand. We have found that it is going to be related with the change in wavelength also. My change in frequency will cause what? Change in wavelength. So here in Doppler broadening, if the atoms which emit radiation at the rest, if it moves with certain velocities and different direction of motion, we find broadening to occur. We call that as Doppler broadening. And coming to second, collision broadening, as the name gives us, at the time of emission, if an atom undergoes collision, there will be a change in phase shift and frequency shift, okay, causing broadening to happen through. We call that as collision broadening. And the last, natural broadening. In solid materials, okay, the emitting energy is in the form of photon, leads to an exponential damping of the amplitude of the wave train, and the phenomenon is called natural broadening. If I have an active medium, so far we have discussed about the active medium and the lasing medium, where the atoms are going to be put into excited state and lasing action takes place. We call that as active medium. Now, if my active medium is a solid material, okay, you know about how the material composition and atomic structures and molecular structures will be in solid and liquid and gaseous materials. Okay, how the bonds will be interlinked between solid materials, rather than compared to that of a liquid and gaseous materials. Clear? And in solid materials, we find more bonding to be present. Okay, and even though if I apply optical pumping and after excitation, even if my lasing action takes place, the atomic electron emitting energy in the form of photon will have exponential damping to be occurred because of the molecular structure of the solid material. Okay, and the amplitude of the wave train reduces. Okay, it will affect my amplitude of the wave train, and this phenomena will be called as natural broadening because of the material nature, and that too because of solid materials. Okay, so that is what you need to understand. So we have seen about directionality and divergence. Both are related one way, directionality and divergence. A beam which is less divergent will have more directionality. So if I want to find the divergence phenomena, we can relate that to the outer edge angle with that of the axis twice the value, correct? Or we can say it as in terms of two distance measurements of diameters d1 and d2. If I find a1 and a2 to be the diameters, I could relate it as psi is equal to a1 minus a2 divided by 2 times d1 minus, sorry, d2 minus d1. Okay, a2 minus a1 divided by 2 times d2 minus d1. And if the beam is less divergent, we find more directionality to be present. Clear? And that is how it is being related with directionality and divergence. Okay, and my laser beam will have less divergence to be present. Okay, and coming to monochromaticity, monochromaticity is about a particular wavelength to be produced, and this change in wavelength will be because of phenomena of change in frequency. That is how it is being related with. So this change in frequency may happen because of three kinds of broadening. That is one, Doppler broadening, where the excited atoms which is going to emit my photon will happen to move at different velocities and direction. It may cause a frequency shift again, followed by broadening. We call that as Doppler broadening. And coming to collision broadening, as the name gives us, collision is going to take place at the time of emission, which causes a change in a frequency shift, phase shift, accompanied by broadening. Clear? We call that as collision broadening mechanism. And the last is going to be natural broadening. This is because of the material we choose it. In solid materials, we find natural broadening to occur because of the material composition, how the atoms are aligned in a solid material when compared to the rough liquid and gaseous structure. Okay, material structure. So this is what monochromaticity is, and directionality and divergence. Is that clear for everyone? Any doubts? Find any? Clear? Yes, no? Answers please. I do look for answers. Clear? So is my voice audible? Yes, okay. Thank you. Now coming to coherence. And we might have seen some phenomena related to coherence. And if we say coherence to be a phenomena of laser action, a laser beam is going to be accompanied by different photons to be emitted of similar wavelength, and those wavelength of photons is going to flow in phase. Okay, and we call that as coherence. To be in more precise, we have two classification of coherence to be present. One is going to be temporal coherence, and the other one will be stated as spatial coherence. Clear? So when we talk about temporal coherence, what is this temporal coherence is? So it is correlation of phase or correlation in phase with respect to a given point in space over length of time. So what you need to understand is, if I happen to have, I will show you. I will put up a window before you so that it will be easy for you to understand things here. So the first temporal coherence, what you need to understand is, if I find a phase to be present at particular time, and if I compare the amplitude of the phase with another time interval, okay, of the same line, okay, of same photon emission, and if I happen to see the same value of amplitude and phase to be present with all time intervals, all of my time intervals, we call that as the wave to be temporally coherent. Okay, and as long as there is no deviation to be present, if I measure the value to be same, say for example they have measured here. See, kindly look at the screen share. They have measured the phase and amplitude here. At the same time, at another at another time interval, they are trying to measure the same kind of peak. And if they have the same value to be present, okay, we call that as temporally coherent. That is, we happen to have a wave, and in that wave pattern, if I measure the phase and amplitude at different time intervals, if I happen to have a similar amplitude and magnitude to be present, we call that as temporally coherent. Okay, And as long as it does have this temporal coherence, the length until there is no change in phase to be accompanied by, we call that as coherence length. So after coherence length, you will find change in phase or the amplitude will change. So that is what you need to understand here. So this coherence length is going to give us what? How long time interval it is going to have a similar kind of pattern. Okay, so this is what temporal coherence is. And coming to spatial coherence, coming to spatial coherence, okay, coming to spatial coherence, it refers to the correlation in phase at different points at the same time. See, again, we are going to uh, find the correlation in phase. It refers to correlation in phase, but at different points at the same time. Say, for example, if I have multiple wavelengths to be produced, that can be shown here. Um, in the previous and the next slide, you can find the x, y, z point are going to remain same, okay, for a single wave. The time changes for temporal coherence, that you might understand. So the time of sampling T1 and T2 is going to change, whereas my XYZ plane coordinate is going to remain same. Whereas in spatial coherence, you might see that it is going to make a comparison between different wave fronts. So we will have similar wavelengths, but different photons will be associated. And if I have an array of photons of similar wavelength to be produced, I will compare all the x1, y1, z1 with that of the x2, y2, z2, with that of x3, y3, z3, but at the same time interval. Clear? So if that wave comparison has been made, and if I find correlation in phase, we call that as spatially coherent. Okay, so that is what you need to understand is clear. So I will show you a diagram now. So that might explain you in detail. I will put up a diagram so that you might understand spatial coherence, what it is. So now a screen has been showed to you. It has been shared. This diagram represents what spatial coherence is. So you might find the phase to be same for all these waves. Okay, they are of similar wavelength. So I find the correlation phase to happen at to be remaining same for all these wave conditions. Clear? So we call that as spatially coherent. Okay, and I've shown you a condition for what temporal coherence is. These are the two phenomena that accompany my characteristic phenomena of term coherences. Okay, so what you need to understand is coherence is expressed in terms of ordering of light field. Okay, and it is accompanied by temporal and spatial coherence. So temporal coherence is correlation in phase at a given point over length of time. So my time changes, T1 and T2 changes, but I'm talking about a single wavefront where X, Y, Z is going to remain same. Okay, and I will check for the phase difference between different time intervals T1 and T2. And if it is going to be correlated, we call that as it is temporally coherent. Okay, the high degree of temporal coherence arises from laser's monochromaticity. Okay, my laser is going to be always more temporally coherent and also spatially coherent. Okay, that is what the conditional phenomena for laser to occur. So that you need to understand first. So to be in more detail, we talk about with respect to different time intervals for a single wavefront, and in spatial coherence we will talk about multiple wavefronts, but for single time interval. So you can find the difference now. So what you need to understand is if I take a single wavefront and if I compare the phase difference at different time intervals, we call that condition to be as temporal coherence. Whereas in spatial coherence, we talk about different wave fronts that will be compared with a similar time interval. Okay, so that is what spatial coherence is. Hope I made this clear for you. Yes, no answers, please. If not, do tell me. I will put it. Try to teach it again. Clear? Yes, no answers, please. So you must have understood about spatial coherence and temporal coherence, what it is. Is that clear for everyone? Yes? No? Okay. One answer. அப்போ அதை மற்றவங்களை கவனிக்கிறீங்களா இல்லையான்னு எனக்கு தெரியலையே. ஓகே, சரி, தேங்க்யூ. So the last topic or last property that is going to get associated with the laser is going to be intensity or brightness. So this might have been stated before. The intensity or brightness is going to be related together, and my laser will have more intensity when compared to that of a sun. That is, an example might be quoted. I've been quoted before to you, where a 1 milliwatt helium neon laser is going to have 100 times more brightness compared to that of the sun. Okay, this is because of the coherent nature. So what you need to understand is the properties of a laser, even if it is a monochromaticity, or we can say it is directionality, divergence, and all of these four parameters are going to be one way related. If my intensity, if I am talking about intensity and brightness, it is going to be related with again directionality and divergence. If I talk about directionality and divergence, it is going to be related with monochromaticity. If I talk about monochromaticity, again it is going to be related with coherence of nature. Clear? So all these four parameters are again interdependent. Clear? So when what you need to understand is when two photons of each of amplitude A, say for example, if I have two photons, each of amplitude A are in phase with each other, then the intensity is given by simply, it is going to be I, denoted as I, proportional to 2 times A square. So what you need to understand is my photons each of amplitude A, if I have two photons to be present, my intensity will be proportional to 2 times the A square value, that is 4 times A square, 2A the whole square, which is equal to again 4A square. Similarly, in my laser light, I might have many number of photons to be present, n number of photons to be present. Then my I proportionality will be equal to what? N square times A square, or Na the whole square. So the resultant wave intensity is going to depend upon what? The number of photons to be present and the amplitude of each photon. I happen to create a laser action. Since laser action is produced, I have photons with similar amplitude. Clear? So the photons which are being generated from lasing action will have similar amplitude pattern. So I will represent as simply A. And if I want to find the intensity of that photons that are generated, if I happen to have n number of photons to be present, my intensity will be proportional to what? Na the whole square, or we can say it as n square times A square. Clear? So this is how you need to understand about intensity and brightness. More the intensity, more brightness will be produced. Okay, and intensity and brightness will be again related with what? Coherence. If I have more coherent beam to be produced, coherent wavelengths to be produced, which accompanies both temporal and spatial coherence, I happen to have what? More intensity and brightness. Clear? So that is what you need to understand from intensity. So we have discussed about 4 parameters today, starting from directionality and divergence. Then we went for monochromaticity, where we talked about the change in frequency shift related with change in wavelength. Clear? After that, we have discussed about Doppler broadening. Then we discussed about collision broadening, and the third one as natural broadening. Clear? After, we went for the next characteristics, that is coherence. You know what coherence is. So under coherence, we dealt about spatial coherence and temporal coherence. Clear? So temporal coherence na என்னன்னு புரிஞ்சிருக்கும் உங்களுக்கு. நான் மறுபடியும் சொல்ற விஷயம் இதுதான். இது லைட்டா கொஞ்சம் குழப்பமா இருக்கும். இப்போ டெம்போரல் கோஹரன்ஸ்ன்றது ஒரு வேவ் ஃப்ரண்ட்ல அந்த ஒரு வேவ்ல இருக்கக்கூடிய ஃபேஸ் அண்ட் சேஞ்ச் இன் ஆம்பிளிடியூட். ஓகே, அதை நம்ம டிஃப்ரெண்ட் டைம்ல அனலைஸ் பண்ணி பார்ப்போம். அப்போ டிஃப்ரெண்ட் டைம் இன்டர்வல்ஸ் T1 T2 எந்த டைம் இன்டர்வல் எடுத்துக்கோங்க, மேபி T3 T4 கூட எடுத்துக்கோங்களேன். அந்த டைம் இன்டர்வல்ல இஃப் மை ஃபேஸ் அண்ட் ஆம்பிளிடியூட் இஸ் கோயிங் டு ரிமைன் same. Clear? So we call that as temporally coherent. When we talk about spatial coherence, we talk about a similar wavelength carried by different photons. So we have number of photons we've generated, and all those photons will have similar wavelength and frequency. Okay, and photon which compare பண்ணும்போது different photon levels different இது compare பண்ணும்போது we are talking about similar time of sampling. We will compare change in phase and amplitude, but with different photons. Okay, that is what you need to understand from spatial coherences. If my laser action has more temporal and spatial coherence, it automatically accompanies more intensity and brightness. That is what you need to understand. So intensity brightness ஜாஸ்தி இருக்குன்னா அது காரணம் coherence nature. Coherence nature again it is going to depend upon monochromaticity. Again monochromaticity will be accompanied by directionality and divergence. So all these four factors, the characteristics what we have discussed today are interdependent. Clear? Yes? Answers please. புரிஞ்சுதா? Understood? Yes? No? Answers. My dear students, please do answer so that I could come to a conclusion. Yes. Okay, thank you. Then we are going to find the difference between spontaneous and stimulated emission with respect to the characteristics of laser. Okay, and the property we are going to have is first on a stimuli. We know that spontaneous emission doesn't require any stimulus to be produced, and stimulated emission we require stimuli. Okay, and monochromaticity less, whereas here it is going to be high. Directionality is less, where it is going to be high. Intensity is going to be less, it is going to be high. Coherence less, again it is going to be high. So what you need to understand is in spontaneous emission all these four factors are going to be less: monochromaticity, directionality, intensity and coherence. And if it happens in stimulated emission, we happen to have all these conditions to be high. Okay, and spontaneous emission doesn't require any stimuli, whereas a stimulated emission requires a stimuli, and the stimuli comes from spontaneous emission. So one spontaneous emission is going to trigger all my characteristics accompanied by stimulated emission. Clear? So that is what you need to understand here. Clear? Okay, now thing about pumping, we have different pumping actions to be produced. So here we have a 3-level laser and 4-level actions, 4-level laser actions that you could easily understand. So this is not practically possible. We cannot achieve a population inversion practically in 2-level laser. Here and here we can achieve a practical means of population inversion. But what you need to understand is where lasing action takes place. Here you can see my lasing action is between E2 and E1, but it is theoretical. Whereas coming to a 3-level laser, you find again lasing action between E2 and E1. Okay, but we have an intermediate level. This is going to be the metastable state. Whereas here you find 2 intermediate levels, and my lasing action takes place between E3 and E2. Clear? Okay. 2-level, 3-level and 4-level system. Okay. There are different types of pumping that is available. Clear? So we have optical pumping, we have electrical pumping, we have even chemical pumping also. So the pumping action is nothing but making my atoms which are present in the ground state to move into the excited state. That is my action of moving an electron and atom to an excited level will comprise of what? Atom to get into an excited state. So here if I talk about an electron or atom, both are going to be same. So an excited electron or excited atom will move into the excited state or at the top level when I provide the sufficient energy. and the process of providing such energy will be called as what? Pumping here. So we have different types of pumping to be present. Okay, in that the very basic means of pumping actions will be optical and electrical. Okay, by giving an high energy flashlight to be produced, even if it is plus or continuous operation. If I provide it optically by means of supplying a photon of energy, we call that as optical pumping. Clear? Electrical energy. The same, if it is provided in terms of electrical energy, we call that as electrical pumping. And we can find that in semiconductor lasers. Clear? So this is what you need to understand. Then the pulse lasers, depending upon the laser's nature, which is produces an output, we have three types. One is normal, another one is Q switch laser, mode lock laser. Normal lasers are less power. Q switch lasers will have more power to be accompanied by. And when we talk about mode lock lasers, we are talking about short duration pulses, very short duration pulses. Okay, that is well associated with high energy. Okay, we are talking about pulse lasers. So in pulse lasers, we have three types. One is normal pulse lasers, second one is Q switch lasers, and third one. So in normal lasers, the power is going to be less. In Q switch lasers, we happen to have or create more power, high power. Okay, and third one, mode lock lasers. It is about creating a more power lasers of very short duration, and it is going to have uh, a mode lock phenomena. That is, my pulsation width will not change. It is going to be locked to a particular time. Okay, that is what you need to understand. Then, okay, coming to other differences of spontaneous and stimulated emission that you need to know. So we talked about the differences between spontaneous and simulated emission in terms of the four characteristics. Clear about directionality, divergence, monochromaticity, coherence, and intensity. Here, when we talk the other terms of differences, we call the first point to be as polychromatic radiation. In spontaneous emission, there cannot be again monochromatic radiation to be possible. Again, the same things are going to represent it in a different way. See, polychromatic radiation, here monochromatic radiation, again less intensity, whereas here high intensity, less directionality and more angular spreading, high directionality and less angular spreading, spatial and temporal incoherent radiation, here spatial and temporally coherent radiation. Clear? So again, the same difference, but in terms of different words. Clear? That is what you need to understand. The same thing about spontaneous emission and stimulated emission. அதில் சின்னதாக உங்களுக்கு லெஸ் மோர்னு கொடுத்துருப்பாங்க அதை இங்கே சென்டென்ஸாக கொடுத்துருக்காங்க. தட்ஸ் இட். தட் இஸ் வாட் யூ நீட் டு அண்டர்ஸ்டாண்ட் ஹியர். கிளியர்? ஓகே. So we will stop here exactly and we will continue in the next class. Okay. Dear students, if you have any doubts, you can ask me now. Is that clear for everyone? So we have studied about the characteristics of laser today and a certain introduction about different pumping actions we have completed. Clear? Any doubts you have? If yes, do post it in the chat box. If not, you may unmute yourself and you can say it. Clear? No problem at all. Any doubts you have? So I'm going to complete the session. Shall I close my session? Any doubts? Do respond. I look for response. Yes, no, answers please. Okay, thank you. Shoguru sir.
வந்துட்டேன் சார்.
Sir, continue பண்ணிங்க sir.
சரி, ஓகே.
Okay sir.